mechanical parts. So that was especially important, first of all, in the 19th century, when very much machinery was introduced. Let's say, for instance, the steam engine, the railroad, and in connection with that, there were many accidents which were not really understood. That is, for instance, something like a shaft or a screw, and what you can see is a part of that is separated by a phenomenon called fatigue, and that weakens the part, and when it is too weak, it will fail, as we say, catastrophically. That means it suddenly fails immediately, but the complete process of failure has taken considerable time. And there are such examples, for instance, for wind turbines, or here that is a jet engine. What can happen here is that one of the rotor blades is getting loose, for instance, because it is the support is breaking, and such a turbine has let's say 10,000 rotations per minute, and that means centrifugal forces are considerable, and they cannot only destroy that turbine, but they can destroy the complete aircraft if they don't go to the outside, but inside the aircraft. So that's something which is very, very important. When you look for fatigue, you find very many answers, for instance, in Google Scholar. Of course, fatigue is also a phenomenon in psychology or in medical science, but here we talk about mechanical fatigue. And it is said that fatigue is responsible for more than 90% of all mechanical failures. Today we are going to deal with fatigue. So that is what you see here is an accident that was at the end of the 1990s in Germany, somewhere here near Hanover, in northern part. And here an ICE crashed. You see it crashed completely. And that was also a fatigue problem. Let's say, the strange thing is that people thought fatigue was in railroad applications was mainly solved by end of the 19th century. Also, the theoretical foundation for treatment of fatigue was given, but anyway, 90 years later, again, such an accident appeared. Here you can see in more detail. Here's a small house. They have a garden, and suddenly you find such a car of the railroad in your garden. Here is a bridge. That bridge collapsed. That was the main thing which made the accident so severe, that the bridge collapsed on part of that train. But now let's have a more detailed description. So that was 1998, an ICE. It was ICE first generation. It had a speed of roughly 200 kilometers per hour. And what it had was a broken wheel. That wheel was, let's say, a two-part construction. That's a railroad wheel. Maybe it's more round than here. on the other hand, also a wheel gets some kind of wavy on the surface, so it gets some ripples. Also, the rail gets some ripples, and so from time to time it's turned down to make it smooth again. Otherwise, the ripples lead to much noise and discomfort. Also, here in between is some rubber layer, and that rubber layer leads to the fact that the contact area has only a limited thickness. Yeah, and now when it's turned down, it becomes thinner and thinner. And on the other hand, from the backside here, cracks developed. People knew that such cracks could come. Also, they had installations in order to do ultrasonic inspection for that. But unfortunately, that system turned out it was not useful. Yes, it was unusable. And so they just didn't do that ultrasonic inspection. And that led to the fact that this crack developed. And now when you have a crack and you have a thinner ring here, it becomes weaker and weaker. And at some during that train ride, the train was driving over a switch, and the switch always means increased force peak, yes. And here that ring broke, and that breaking of the ring led to derailing of the complete wheel or of the axis at the next switch. And just when that train, I think the second car, was under the bridge, the whole thing derailed so much that the pillar of the bridge was hit and it was destroyed. And so the bridge, which was made of concrete, it fell down on the train, and so the rest of the train was more or less destroyed by hitting this broken bridge. So that was the chain of actions. You could say there were many aspects, but in the end, it turned out it was a fatigue problem. Also, what I think as an engineer is what makes me a little sad is afterwards that the whole thing went to court and nobody was found guilty. Yes, so it was treated like, you could almost say, bad luck. Yes, and I would say bad luck is nothing where we could say in engineering that is justified. Yes, typically someone made a mistake. Yeah. Or it was some omission of something, like here, omission of the ultrasonic inspection, and the whole thing. The result of that judgment, I think it was predetermined, because the Attorney of State didn't accuse the people who omitted the ultrasonic inspection. Yeah, so the whole thing was. When that wheel got clearance for being used on an ICE train, part of that clearing meant it has to be inspected regularly. And so, of course, now when someone doesn't inspect it, yes, I don't think you can blame the guy or the group who constructed it. Yeah. And so the whole thing, I think it was some also political will not to proceed with that because at that time ICE was some prestige project in Germany. Okay. The main thing was the following. First of all ICE trains were limited in speed for considerable time. Also for many months, the number of passengers declined significantly. The technical actions taken, I'm sure there were some taken, but it didn't become public. Also, there was no, let's say, so consequence insofar as we have to improve the system or so, yeah. So generally, I think, yeah, how to say, if just for a railroad wheel, you can say that was bad luck, yes. What will you say when something happens in a nuclear power station, yes, which is much more complicated, yeah, that here that was one mechanical part failing. And so I think that is something which should not have happened and that could have been avoided. Okay, here the background you have in the lecture notes. And now let's have a look, what is fatigue? So normally when we have, when we test materials, we take, for instance, some rod for testing and we pull on it. Typically, we pull with a constant velocity. That means a percent of strain per minute or something like that. And so you could say over time, over strain, the load goes up. And normally that you, in almost any material, you reach the ultimate tensile strength. And then it's tearing, and then somehow force goes down because it's ripped up. And that can depend on the material. For instance, that material has a higher Young's modulus, and it's evidently a material which doesn't have so much plastic deformation. So that's normally how materials are tested. And that's the first thing that you say, okay, if a part is weaker than the force it has to tolerate, then of course it's no use, yes? It would break immediately. You sit on that chair and it will break down. So that's first of all, that's the first design criteria. Then we have some other behavior. For instance, we put on a certain load, and that load or stress is constant over time. Look up that lamps, they hang on something, yeah? You could say that's that behavior. The string on which it hangs, it is, yeah, it's over the years, it's at a constant stress, yeah? And here you could say, yes, for the lamps, evidently the strings are strong and the weight of the lamp is low. So you could expect it will hang there forever, you could say. If the stress you have at a constant level is closer to the ultimate tensile strength, it could mean that after a certain time it will fall down because it breaks, yeah? That is the time to rupture phenomenon. The material deformation is called creep, yes? Material can also become longer and longer over time, but at some time it ruptures, and then you have that behavior over time. We will not treat that anymore, but in assembly and packaging, it can be important. Now we talk about fatigue. Fatigue means, first of all, we have some alternating stress, and that stress has a certain amplitude. Here, the amplitude is not from the mean to the peak, but no, it's not peak to peak, but it's from the mean to the peak. Also, that already could be relatively similar to that railroad wheel. So you could say we have a revolution of the wheel, and as a train has a more or less constant weight during one ride, you could say we have an alternating stress and a superposition of a constant stress, for instance, by the weight. In fact, when you look at that, you can still improve that behavior. You can say, okay, the train is driving slow and fast, and so if it's slower, forces will be lower, yeah, just due to dynamics. And that means you can have such a behavior. Again, here the mean is the same because the weight of the train doesn't change much. But now imagine you have a freight train transporting, let's say in Sweden, iron ore or such a thing. Then you could say when it's empty, maybe you have that behavior. It's full, you have that behavior. And that means we have variable loads. And now the important thing is that the variable loads, even when they are significantly lower than the ultimate strength, they will lead to failure after a certain time or after a certain number of such alternations of phases of such stress. So that's the behavior. I would say that's the most general. Maybe there are also other cases, for instance, where the mean could become negative, for instance, in an aircraft wing, yeah, and so it's quite complex. And so question, will the loading type have an influence on lifetime and reliability? We have constant, monotonic, cyclic, or variable loads. What is a correct property which describes the load here? And what is fatigue also? That could be questions in an oral exam. And yes, the load on a part is normally measured as a force in Newton. When we talk about materials loads, we talk about mechanical stress, which is force per cross-sectional area. And in that way, we are on a level where we can, where the strength of the material is relevant and not so much the breaking force of the part, because that is size dependent, yeah. And in that way, typically properties in mechanics are treated on the base of stress, Newton per square millimeter in German, or megapascal in English or international. Okay, fatigue. I already mentioned it, and there is another phenomenon which also was important in that failure of that wheel. That's the following. I already mentioned cracks. Cracks have two effects. One is just when you look here, by a crack, the cross section becomes smaller. Yeah. So you could say the force at which something breaks is something like, so when you take that here, stress is force divided by area. And now if the area is smaller, the stress is higher, and the stress can become more than the ultimate tensile strength. Okay, that's a simple part. Smaller is weaker, yeah. But on the other hand, now make experiment, and you take a rod which has a cross section, and you have this part here, and inside that ring-shaped notch, you have the same cross section like here. And now the question is, which can tolerate higher force? Which one? Sorry? Yes, and why? Yes, that is correct. And as we can see here, here's already the stress. At the tip of a notch, we have a stress concentration. And now when a notch is something done artificially, yes, for instance, when you do machining, turning operation, or so you can make a notch. Sometimes you need a notch. For instance, you put around some holding ring or such a thing, yeah. But the ultimate notch with respect to stress concentration is a crack, because what is really important is the tip radius here, and the crack is just a separation on an atomic level. And that means the radius is ultimately small, and very small tip radius means high stress concentration. And that is something important. Also, for instance, when someone is doing a mechanical construction, and sometimes you need a notch, yes, or a step in your diameter, you should not position that notch in a location where the maximum stress is, but you put that in a location where stress is smaller, yeah. And if it rotates, you always get tensile compressive, yes, if that rotates. But sometimes you are able to put some notch in a location where you just have compressive stresses. And the good thing is notches and cracks only increase stress when you pull or when you shear. But again, that's not so important for us in pulling, or let's say in tensile mode, then it's most dangerous. Okay, here that is some simulation one of my PhD students did. Here in the material, we have a stress concentration, and we have, as I mentioned, in tension, we have such an area here where we have maximum distortion, but the stress is something like proportional to the inverse of the distance from the tip. Yeah, R here is the distance from the tip, and a second parameter is the stress concentration. That mainly is depending on the size. That means how big that crack is in that direction. Yeah, so also here it makes a difference if that notch or the whole material goes more to the side, or if it's just a little to the side here. So larger is worse, you could say. Okay, that's the stresses in the stress field in that's a stress field in shear mode. And you can see in all cases, for instance, here you have stress concentrations of that's an increase of more than 200%. Yeah, it can be significantly more, and that's the main reason why cracks are dangerous or notches are dangerous. Here, that angle, in fact, that's the angle under which, when you go from the tip, under which angle you go, is an influence. Here in the most important, which is just tensile, you could say in the direction of the crack, or better, perpendicular to that direction, you have the maximum stresses. And here as it's shear, it goes more something like 45 degrees or around that, yes. And that's in fact that's the angle here between the crack direction and the direction in which you look here. I would not go into details because there are other lectures, especially on fracture mechanics, and so that's not the aim here, but it's more to demonstrate to you that there is a big effect of such cracks. And again, here is that angle. We don't need that formula really. What is maybe more important is, so we have a stress vector. That's just when we take a 2D cut. So we have sigma x, sigma y, and some shear stress that all can be described by the so-called Snedden equations. Snedden was an Englishman who did that analytical calculation, I think around 1920 or so. And what is important here is, I said, the stress is proportional to the inverse of the square root of the distance from the crack tip. But on top here, you can say the stress scales with the nominal stress. That's just force divided by the complete area, multiplied with a factor that is P times square root of the crack length. And in that way, that defines the stress intensity, and that defines the position around the crack, and in that way, that stress field can be computed. Okay. Generally, you can say that stress concentration, as you see it here, and having these geometry factors, can be described for all, let's say, representative cases. That's nominal stress multiplied with P times the crack length. So that's the length from the surface of the part to the tip of the crack. And Q is a geometry factor depending on the special case. And let's say for us here, we say Q is by definition 1, but it can be between 0.7 and 2.5. And in that way, we have another failure criterion. So normally we say when the normal stress is higher than the ultimate tensile stress, then it will fail. But if it's a part that has a crack, then the part will fail when the K1 factor is larger or equal to the K1 C factor. Ultimate tensile strength is a material property. And the K1C, you can call it the critical stress intensity, but it is also called called fracture toughness. That's a material property. So again, you have a criterion: is the load higher than the strength, it will fail. Yeah. And now if you have that load strength concept, you can say, depending on what material is, depending on do I have a crack or not, I take another physical property for load and strength. Yeah. There are also some cases where we do not use something like stress, but we use strain, for instance. Yeah. We also can have energy criteria, but again, to the left, that's the load, and to the right, that's the strength, and the strength is always the material property. And that criterion is, it looks simple, but it is extremely helpful. Okay, here we have some examples. In fact, I'm not really working in mechanical engineering, but we did lots of work on strength of silicon. What's the strength of silicon? Does someone have an idea how many megapascal can silicon tolerate? What do you think? Maybe we start with something different. That's also something you should know. You sit on a chair, and that is made of some steel pipe. Yeah. The strength of such a steel pipe in megapascal or in Newton per square millimeter. What's the strength of such steel? Give me a value. Let's make it another way around. You have a string of steel wire, and you hang it here from the ceiling, and you put on a weight, 1 square millimeter of steel wire. How many kilos can you hang to it? Sorry? Yeah. Just give me an idea. Okay, that's a good point. 50 kilos, that's 500 Newton. Yeah. Okay. 500 Newton is a typical strength of a constructional steel. Yeah. So you can say all steels that still can be welded, they have such a strength. If it's a higher strength steel, normally you cannot weld it, so it can go up to 1,500 Newton per square millimeter. So you could say a quite fat person of 150 kilo could hang to that wire of 1 millimeter square. That means diameter of 1.2 millimeter or so. And so that's relatively strong. Yeah. Now silicon. What is the strength of silicon compared to that? Can be. But the correct answer would be, it depends on the crack length. Yeah. Yeah. Here, for silicon, you can say you have a fracture toughness. You find different values. Also, the crystal direction has an influence. So here we have taken 0.85 megapascal square root of meter. Yeah. And now we take that formula, and here we take for the Q factor 1.48. Yeah. Somewhere in between 0.7 and 2.5. So, and now we have that value, K1C, and now we put into that formula the crack length, and we put it in. Normally you should take meter, but here I have taken micrometers. So if it's 1 micrometer, the silicon will break at 700. Yeah. If it's really smooth and polished, it can break at 3000 or so. And now you have a crack of 30 micrometer. That silicon will fail at only 130 Newton per square millimeter. That means having something like a crack or even just a scratch on the top that will degrade the strength. It's similarly important for glass, for instance, window glass. Yeah. How is glass separated when you have a big sheet and make a smaller sheet? What is the ancient type of, yeah? No. How do they do it traditionally? They scratch it and then they bend it over an edge, yes? And then from that scratch on, it will break, and it will break really easy, yeah? That's the way, and that's the same principle. Also, window glass has a similar fracture toughness. Has a similar fracture toughness like silicon, for instance. Yeah. Many say the most important part for silicon is that it is separated at crystal planes. That is partly correct, but the most important part is that low fracture toughness. Yeah. On the other hand, a quite tough steel can have a fracture toughness of 200 megapascal square meter. So, okay, so that is a crack is something dangerous. And the second is we have the phenomenon of fatigue, and fatigue means we cannot just assume the ultimate tensile strength, but the value of strength which is tolerated is significantly lower. And when we still have a crack, it's lowered again. Okay. When we look at materials, we can say on the x-axis, it's a strength. Here, we do not take the ultimate tensile strength, but we take the yield stress or the yield strength. Do you know what yield strength is? So imagine you have a paper clip of, yeah, you know that paper clip, and you bend it. You can bend it a little and it snaps back. Yeah, that's its task. Yeah, you bend it too much and it snaps back only partly. Yeah, you have, and that means you were beyond the yield point of that material. And still, when you really deform it, then you could break it. Yeah, and the question is, why is in many constructions not the ultimate tensile stress used, but as a design criterion, but the yield strength of that material? Why is it so? No, do you have other ideas? Imagine, for instance, something which we still have is a combustion engine. Yeah, you have the complete system of valves and so, yeah. And now you have a valve or the camshaft or such a thing. And in that part, you exceeded the yield strength. What will happen then? Yeah. yeah, the size will be changed, and that means precision parts, for instance, they do not function anymore. Yes, they are not really failed, but they lose function, and loss of function is also a failure. Yeah, and in that way, many parts, or imagine you have a turbine blade, and when the turbine blade is inside some pipe, yeah, in order to avoid losses of gas, so there is a small gap which is extremely small, yeah, small tolerances. Now, imagine due to some effect, the turbine blade becomes a little longer. Then it will scratch, yeah, against the wall at 10,000 RPMs or so. Also not so good. And that's the reason why yield stress or yield point or yield strength is often taken, because most parts are damaged then. And the second part is fracture toughness. So you could say there is a correlation between strength and fracture toughness. You could also think about fracture toughness, something like the energy a part can take when it has a crack and you overload it. Yeah, that would be a different understanding of fracture toughness. And here you see the strongest materials, at least from the metals, are the steels. And also what is very good for them, they have a really high fracture toughness. Talking about the valves, my colleagues in Mercedes, they were developing valves for Mercedes cars, for high power cars, which were made of silicon nitride. Yeah, so you can say they are stronger, but their fracture toughness is a factor 30 or so lower than for steel. So if you have a small scratch on that ceramic material, it will break. Yeah, the strength is high, but as soon as you have a crack or a scratch, it will degrade totally in strength. And that was the reason we had test cars running. The valves were made in a clean room, like you do semiconductors, yeah, in order to avoid micrometer size particles in that silicon nitride. It had to be polished. All of that worked, but in the end, from time to time in the test operation, some valves cracked. And if you have an engine running at 6,000 RPM, that's also considerably annoying for the driver. Yeah, and in that way, in German you say the motor platzt. Yeah, it really destroys itself, and that's the reason why we often prefer materials with fracture toughness. Also, where we can say where it's really helpful. What is the material we use for making car bodies? Most cars still, what are they made of? Steel, just steel. And the reason is steel is a material which can take most of the energy when you crash. Yeah, we have a strong passenger cabin, yeah, that protects you, but you have a crash zone in your car, maybe up to a meter or so, and that saves your legs, and it also reduces the G-forces. Yeah, the more length you have, the lower the G are, and in that way you can say that's good for steel because it can take lots of energy here. And so we see steel, they are material 2,000 years old or so, but they are still state of the art and really important. Aluminum can be taken, but it's rather taken in areas where you want to have low a low weight and high strength, for instance. The ratio is better, maybe. Also, it can be better for titanium. The best nowadays are carbon fiber reinforced polymers. You can see that on Formula One race cars, for instance. Up to the 1970s, every season, a few race car drivers were killed. Yeah, and that doesn't happen anymore. And one of the main reasons is the carbon fiber reinforced so-called monocoque construction, which is extremely strong and which can also be built in a way it takes up a lot of energy. And in that way, that's some safe construction. Okay, we have seen that with the notches. I will go over that. That's not so important. But now let's come to fatigue. There are two persons which are important in, let's say, in the Anglo-Saxon area, it's Mr. Baskin, and in Germany, it's Mr. Wöhler. And Wöhler did his work between 1870 and 1890 or so. And he worked in some office that was part of the railroad system. And the main problem at that time was three: breaking of axis, breaking of wheels, breaking of rails, and the fourth thing is explosion of steel vessels. Okay, the last is something like action of a bomb, you could say. Okay, and that was, all of that was due to poor understanding of materials, not understanding of the effect of cracks. Also, steels at that time were quite bad. They had many inclusions, and the internal inclusion is same like a crack. Yeah, that was important. And by 1870, people didn't know nothing about fatigue. And now that Mr. Wöhler, he started from scratch. And first of all, he thought about what it might be, and he built a machine in order to do dynamic testing. That means you can put an alternating load on a part, and depending on the load, you can determine how often you can have that loading unloading, yeah, or reversion of the stress. Okay, here the initial experiment was just go to a positive and a negative stress. Tension, compression, tension, compression. How do we accomplish that most easily? We can either take some bending bar and having it vibrate in some way, or we take a rod, bend it, and turn it at that time. And so we also get some symmetric tension compression. So, okay, and then Mr. Wöhler found out when you do your experiment, what is the stress level for the stress amplitude you start with? You cannot be larger than what? You cannot be larger than ultimate tensile strength. Yeah, that's clear. And you could also say, when you go to ultimate tensile strength, or better, you go to yield strength, how many cycles will you have? You can have, you destroy it, so you have half a cycle. Yeah, that's not really fatigue, but you could say here your curve will start. Half a cycle, yield strength. And then the stress is reduced, and you can already get, where is my mouse here? Here, you can get on that curve, when you want to investigate the material, maybe 7 specimens around that are already sufficient. And then you decrease the stress level, and maybe you go down to 50% of the yield stress. And in that, you have 7 data points. And when you have that, you get such a curve. That curve has, of course, much scatter, you will see. And it has a slope going down. That clearly means lower stress level, higher number of cycles. And you also should say that's not the number of cycles, but the logarithm of the number of cycles. And here you could say that ND is somewhere 1 million to 10 million cycles. Yeah. And when you have reached that at a certain stress level, you often find that the specimen will live longer. And or when you are at a stress level here below that, it also can live until infinity. That's not the case in every material, but in iron materials, steel, you could find it. And that's a basic representation of the so-called Baskin curve or the Wöhler curve, maybe a small difference. Baskin used also a logarithm for the stress, and Wöhler did the stress linearly, but there's not much of a difference because the stress level only goes over, let's say, half a decade or so. So it's not really something where it makes sense to plot it in a logarithmic way. Yeah. More or less, you often find it. We will see more details. And so generally in fatigue, what happens? Normally, when you load it, you have a crack-free phase when it's a new material. And sometimes, as I said, you have already inclusions. For instance, some oxides or so in steels, and that means you do not have that crack-free phase. But in a good material, you have it, and then after a certain time, you have a crack initiation. A crack initiation means you have some surface profile where the step size of such a profile is in the micrometer region. You can see that, for instance, when you have a polished part of steel, which is really polished, and then after a certain time, you see some kind of weak pattern on the surface. Yeah. And when this pattern becomes stronger, you get a crack, which is more a crack by definition. Yeah, you cannot say here that's a point where it's just that surface pattern, and here that crack. But it's more a sliding transition. But in the end, engineers take something like an engineering crack, which means the part already had become a little weaker. Yeah, a few percent weaker, and that is a crack by definition. And in that way, when the crack has been formed, the crack will grow. And you could say, depending on the stress level, it will grow between a nanometer per cycle and micrometer per cycle. Just it becomes longer. And then when it is long enough and the part is weak enough, it will fail immediately. Yeah. So typically in a fatigue problem, you look at the cracked surface and you always find two areas: the fatigue area and the final crack area. And in that way, that's the phases of crack. And also it's interesting, depending on when we have a component with a crack. So if we have some variable load, it can lead to fatigue or over time to creep. When we just pull, depending on the toughness, we have either a ductile fracture, that means it takes lots of energy, or we have a brittle fracture, then all of the energy just goes into the crack. Yeah? Ductile means all of the energy goes into the complete part. And what we can also have is something tricky. It's an arrested crack. Where do we have cracks? In tension or compression? Yes, in tension. And sometimes in a 3D part, a crack is running into an area where we have compressive load. Yeah, that's when we have a complex stress field. And then the crack is just remaining there because under pure compression, it cannot extend anymore. So that's arrested crack. So we have many possibilities. Often it happens, for instance, we have fatigue in a first phase, and in a second phase, we can have ductile fracture, that's the rest of it failing, or we can have a more brittle fracture, but that depends mainly on the material, and it also depends on the temperature where we have that. For instance, at higher temperature, materials become softer, and so they are more ductile. So that's quite complex. In the end, we already have that curve. We can say that's a Baskin's curve, or it is also often called SN curve, stress versus number of cycles to failure. And that stress level below which a part can live until eternity, that's a so-called endurance limit. And so typically that starts from 1 million to 10 million cycles on, or 10 to the power 6 to 10 to the power of 7. So here you can say, here in the beginning, you have something like, my mouse, we have something like, you have something like the yield strength, half a cycle, and in that way, here you know endurance limit is often somewhere at around 50% of yield strength. So in the end, when you know the yield strength of a material, you already have an idea how the fatigue behavior will be. That's not really precise, but for a first guess, it's quite good. Yeah. Yeah. We have safety factors, and the times when we had safety factors of 2, they are long gone. Yes, maybe they often have maybe 1.5 or such a thing. Yeah, I know it's really long time ago. When I was working in electronics, I said, okay, when you have parts which are highly loaded, you could put on a some strain gauge and measure how it is loaded. And in that way, just by monitoring, you could reduce the safety factor from 2 to a lower value. And that guy who did such constructions, he laughed at me and said, oh no, we don't use a factor of 2 for for a decade or so. And that was a long time ago. So that means also, it also depends on the quality of the construction and the quality of the mechanical engineer, of course. And it also depends on the quality of the machining and the quality of the materials. Yeah. And in that way, that's a fatigue curve. And you could say that was the first step of reliability engineering. So at that time, reliability was defined by, let's say, the fact that you wanted to avoid the catastrophic failure of a single part. Now, here, to give you just an example, that's from one of my PhD students. We had micro parts, so quite small, some dimensions significantly below a millimeter. And so we designed a specimen. All of that C here, that is just to handle it. Yeah. The main part is here where the sigma max is. Here we were interested in the fatigue behavior. And how can you load that in a defined way? First of all, when you look from here to here and you put your finger on here, that pedal, you press it down, yeah, that's a little wrong. The maximum stress is here at the end. And how can you make an alternating stress? We had the idea, put some magnet and load it, unload it with a coil, yes, with just by magnetic forces. That works. But yeah, here we can see it. Here the maximum stress. We pull it down, press it down, and push it up just by that magnet which is put on here. But it is also important, what you cannot see, the amplitude was measured with an optical vibrometer. That was important because otherwise the stress would have been too undefined. Yeah. So in that way, we had very small parts. We can see here it's only a few millimeters. The thickness of that part was only 1/4 of a millimeter in that case. And we did that test. And now he did several steels. When you produce small steel parts, that steel 304 is something like a stainless steel. And in that way, we wanted to investigate what the effect of the machining was. One was etched material, just in an acid with photolithography, and the second was electrical discharge machining. Yeah, you have a wire, and that wire gives a spark against your part, and that spark takes out some cubic micrometers of material, and in that way you can machine it. What you can see, the etched was stronger, the part, than the EDM, but the EDM was somewhat better, so it tolerated significantly more cycles than the etched steel. That's a little strange, because normally you would expect, from what I told you previously, that the stronger steel here that has 1,500 megapascal as a strength should also be better at fatigue. But here you can also say the surface has an influence, and probably that EDM created some, you could say, compressive stresses in the surface. On the other hand, the endurance limit is roughly 600, you could say. In that way, you can clearly see for these two steels this this curve. That point here was 550. I think that was not tested to the end. We just stopped because almost 10 to the power of 10 cycles is takes a long time. Yeah. Our machinery, it could test so many cycles because the frequency of testing was high. So you could say in a big part, you have a frequency of a hertz or 0.1 hertz. But at 1 hertz, you can hardly test 10 to the power of 9 cycles. But at 500 hertz, it accelerates it significantly. Here was something different. A company, so that was something like similar like that 304 steel. That's a German one. Again, here for the good ones, the endurance limit was very similar because it's a similar steel. But here at the higher stress levels, we had a very large scatter. And what happened here, that was a steel which was done by rapid prototyping, by laser writing a steel structure. And we found many defects in that material. And the consequence was you have cracks or internal flaws and so, and that leads to a very large scatter. You could say that scatter here near the endurance limit is almost 2 orders of magnitude in lifetime. Yes, that's of course absolutely intolerable for a reliable part. Yeah, because you really don't know, are you on that border curve here, or are you on the left side of that curve? So that's something which was also interesting to find out. In the meantime, these rapid prototyping techniques for steel parts are significantly better, and that's also necessary. But I always say, when there's some hook to which I hang my life, yeah, it's always a forged hook, not a cast hook, not a rapid prototyping hook. It's a forged, which a blacksmith made, yeah, because that has no internal flaws. Okay, so that's here you again see we had other materials, for instance, because we are microsystems engineers. We did lots of work on copper. Again, here you see copper is